Okay, a couple of things about torque that I forgot to mention the other day when talking about the equation. So the equation on your equation chart has the radius is a cross product with the force. Okay, so it's a cross product. So on Monday, I will do a quick video, or I'll post a video talking about the difference between a cross product and a dot product and how you handle those. Because apparently I thought you guys did a lot of that in calculus, and the kids, in-person kids told me, no, you haven't done a lot with that in calculus. So I'll do a brief overview if you need it, okay? The really important thing is knowing that when you're calculating a torque, that you are calculating it with the force that's perpendicular to whatever object you are applying the torque to. So if I'm applying a torque to this bar here, there's my force. Here is the R. The R is the distance from the axis of rotation. So sometimes it is the full radius, sometimes it's not. Okay, so in the example shown, it would be the radius of this motion. But if I were to put the force over here, then my R becomes much smaller. Okay, so again, it's always the distance between the force and the axis of rotation. So for this example I just did, the torque about that bar would just simply be the force times that radius. Okay, so what we need is that perpendicular force. If I were to take the same bar with the same axis of rotation, but apply a force at an angle, like this, and then I have my angle theta over here. Let me move my force over. Oops. Okay, so if I applied my force like this, then we have to have some components here, okay? So that force has a component in the x direction going to the right, but it also has a perpendicular force component going up that is in the y direction. Your angle would then be over here. So if we were going to solve the torque on this bar, it would be the force times the radius. Again, the radius is the distance between that where the force is contacting and the axis of rotation, which is going to be over here at my pivot point, okay? So this one becomes force times the radius times the sine of theta, okay? So be careful with the orientation. The other thing I wanted to add is that the torque equals force times the radius works regardless of what your shape is. So if I'm applying a force here, I'll have the torque is equal to the force times the radius, but now the radius becomes that little piece. So for this example, you would have to use some trig there to figure out that radius, depending on what else you knew about the problem. This came up in the quiz, so I will go over an example just like this in my video going over the quiz. All right, it also applies to a circular object with a force being applied to it tangentially. And again, that R, or that radius, is just that distance between the force and the axis of rotation. The last thing I want to talk about are torque diagrams. So if you were in AP1 last year, then we did torque diagrams in class, and you use them to do a lab. So a torque diagram is basically a way to show all the torques acting on an object. So similar to a force diagram that shows all the forces acting on an object, a torque diagram shows all of the torques acting on an object. So let me get an example here. So let's say I have this balance beam or seesaw or whatever you want to call it, and I have some people standing on it because they don't follow playground safety. All right, so a torque diagram always starts off with a line to represent the object. So in this case, we are representing the beam, okay? A good way to make sure you're getting all of the torques on there is to draw them on the picture. So this person over here applies a torque. I'm going to call him person 1. And he is this distance from the fulcrum. That's what we call that little thing. The person on the right, I'll just call him number 2. He also exerts a torque on this seesaw. Both of those torques are going down. But if we look at clockwise versus counterclockwise, this would be a clockwise torque, and that would be a counterclockwise torque, okay? But we also have the fulcrum pushing up with a normal force. That's the force a lot of times that gets missed on force diagrams. But we also have a force from the seesaw. Now I'm going to assume that the seesaw is uniform, has a uniform mass distribution, which means that it has the gravitational force, I'll just call it a beam, at its center of mass, okay? If it was not a uniform mass, then it wouldn't be in the middle. It would still be at the center of mass, but it would be at wherever the center of mass was. And they would either tell you that or give you enough information for you to figure out where the center of mass was, okay? All right, so over on my torque diagram, I'm basically going to take all of those forces. I'm going to draw them at their locations. So in the middle, we had the normal force from the fulcrum on the beam. We had the gravitational force of the weight of the beam itself. We have the gravitational force from person 2 pushing down at the end. And we have the gravitational force from person 1 pushing down on the left side. So this is your torque diagram. We're going to do some practice with that next time. I'll walk you through an example in a video. It actually will come up in some of the practice problems I assigned yesterday as well. So look at those and make sure you can work through those. I will post the answer key by Monday morning, but I'll try and get it over the weekend so you can have a little more time to ask questions. I will probably do a Zoom in the evening next week. One of the days. You do have a test coming up on February 11th, so I'll probably do another evening Zoom that week. Remember, the test is cumulative, so it's over everything since the beginning of the school year, okay? All right, if you have any questions, let me know. I'm going to be posting a video over yesterday's quiz, and I will probably post a video with the answer keys to the other practice just to go over some concepts that I still see people struggling with. Let me know if you have questions. Have a great day.